Thank you, Angela, for the introduction. And thank you, Wahid, Alec, and Alejandro for organizing the workshop. I've learned so many things about digitalization. And I'm going to add another dimension of the work is about cyber-physical system. So I have a particular focus on the power management. And when we have limited communication, how we are able to apply the digitalization to coordinate different devices. Before going to the details, I would like to thank all the collaborators. So the talk actually a summary of many different parts of our work. Even some very preliminary work was studied when I was a student. So that's like Sivano, Chang Hong from Caltech, and my current collaborator and student. So I would like to thank all the collaborators. So I would like to start my talk with a buzzword. Like you have heard many things, even from the newspaper, Internet of Things. So we can think it's just a buzzword, or we can really trust is our future. So different people from different backgrounds have a different vision of the Internet of Things. As an authorization and control person, like when I think about Internet of Things, what I have in my mind is we're going to, with the advancing sensing, communication, and computation techniques, we would like to coordinate all the devices, for example, even all the light in the room, everything together. And what we would like to approve, we would like all the devices, once they connected and once they coordinate, they're going to improve our daily life. But the question is, how are we going to quantify our life got improved? As a organization, we can formulate, if we can formulate mathematically. So ideally, we would like to maximize the social welfare. And typically, how we talk about social welfare, we assume people have a well-defined utility function or device has a cost function. And since we're dealing with all the physical device, there is a safe operation. So we would like all the device, whether it's transportation or power systems, we would like to satisfy the operation constraints. So like I write down the sentence in terms of prioritization. So what we can do is we can use the disprioritization to coordinate the device. So if we really coordinate all devices like over the earth, like that's it, I think we even couldn't count how many devices is in the world. So the deprioritization, a general framework, the most deprioritization is assuming the device can communicate, compute, then communicate until people reach a consensus point or optimal point, and then people take action. So this is like most popular framework. I highlight some assumptions we assume: iterative and two-way communication. Like what is directed, undirected, we kind of assume all the device has ability to communicate with each other. So that's online assumptions, and we have seen the application actually a very powerful tool like traffic, data center, sensor network, internet, and power grid. So let's take a deeper look at what's the current state of the communication. So communication has gone through a lot of advancement in the past decades. And this is in the, I searched around to find what the power system communication, and I read so many reports. Even there's so many papers talking about digitalization for power system, for smart grid. But once I zoom into all the report, people are saying, so this is an available tool, communication tool for power system, but is it really available? Even we ask for this room, is all the lights connected or not? It's questionable. So it has a very highly cost, and even we assume that all the communication are available. So this morning, we have a very nice talk from Keith and from Nadine about the communication challenges. Even we assume all the communication are available. And there's fundamental limitation for communication. And I just highlight some list. First is reliability. Once in a while, when we look at the video, it's got disconnected. And we don't want that to happen for the power grid, because if the light turns off now, no one can really hear what I'm talking about now. So all the challenges, and one solution for power grid, the nice thing is, since it's a power grid, everything already connected through the electricity line. So some work have been proposing we can do power line communication. So power line communication is OK for a short distance. Once you zoom into longer distance, even 1 kilometer, the bandwidth immediately decay. So I put all the challenges here. So the question, we are not going to tackle all the challenges one by one. The way we're going to think about the question is, can we really reduce the communication needs when we coordinate different devices? And how much communication is needed? Now the question becomes, how are we going to reduce communication? That's a tricky question is, why would I need communication? Because once I have communication, I know what my neighbor is doing. I can coordinate. If I try to reduce, probably it is hard to coordinate. So there's no magic here. It's just we're going to think about what the problem we're dealing with. There are two tricks we're going to do. First, since we talk about cyber-physical system, it's a physical system. So what the physical systems can provide, it can provide information. So that's the idea actually being used for control for hundreds of years, like feedback control. We are not going to do the open loop control. Based on the physical measurement, we can take some action. But the question is, what kind of information is available? What kind of information can help us to achieve the goal, as I said, social welfare randomization? So that's the first tool. And actually, we have so many examples. Sometimes it's not enough. And we can imagine it's not enough, then otherwise we need a communication. So if that's not enough, we are going another way using mathematics. So how are we going to design the algorithm? So probably we can recover some information by increasing the local computation for each device. So that's the two scheme we are going to use. And since this is like broad topic about cyber-physical systems, I'm not going to talk about like, say, this is a general tool can be applied for all the different systems. I'm going to focus on specific examples to show how this general idea can help. So first one, I will talk about in power grid, the low frequency control, and also power allocation just in a building or in a data center. And second one, we are going to talk about quantization to ask the question, what the minimal communication is needed. So let's look at the first one, low frequency control. As a brief background, since probably not everyone is familiar with power grid. So very brief introduction about power grid. So in power grid, we have a generation, transmission system, distribution system to individual residential household. The overall goal is to make sure supply equal demand. So that's actually like all the fundamental in the power grid for like since the power system has been built. The challenge is why so many people working on power grid or smart grid now is there's so many things in the supply side. In order to guarantee the accessibility or environmental accessibility, we have using more and more renewable energy, and we can see a lot of solar and wind in our daily life now. The question or challenge is now all the renewable energy has a lot of uncertainty. So now we need to take our action faster. A lot of like components, including components, to think about how we're going to incorporate the change in the generation side. Is now we can see smart device, like smart home, like smart charging, smart EV, like Tesla. So now we have all the changes in the distribution side. The question is how are we going to coordinate the load? So I'm going to put this like as a question, what we want to coordinate the load. Fundamental goal, we need to make sure the generation and the load always be balanced. And since we're dealing with physical system, to transmit the power, we need to guarantee the frequency, voltage, that stay in the safe range. So second goal, we would like to keep the frequency deviation small, like make sure the frequency stay around 60 hertz, not going to hurt our system. And the last one, if we ask users to coordinate, we would worry about whether people are really happy to participate in the program or not. So that narrows down to minimize segregation disunity. Again, I kind of put a sentence in optimization formulation. So that leads to a very nice optimization problem formulation, well structured. So like the constraint just means the power balance as individual bus I. So the PIM is generation, and the DI is a load. Omega is the frequency, Pij is the power flow. When we call it as a load, I said it's a load disunity or cost when I change the load. And I would like to make sure the frequency deviation stay around 60 hertz. Now all the variables is the deviation of the variables. So this is a nice optimization problem. And if you assume the C is convex, so many distributed optimization tool can be applied. And the constraint is just linear. So we can use any kind of dual decomposition to decouple the problem to apply the optimization. And actually, there's a lot of paper available. Like for example, a popular tool uses ADMM to coordinate. And the scenario is when the PIM is generation, when generation changes, we would like to design the control on the load. So here is the challenges. when we try to assume we can solve the problem, what the assumption we have is even we solve it distributedly, and each I is a bus I or area. So I know what kind of changes the PIM is. That's give me information how I'm going to coordinate a package polarization. In reality, even water disturbance is unavailable because usually the device or like the generation is not just from one location. From a like campus, there is solar at different location. It's very hard to know the aggregated disturbance information. That's the first one. Even without think about communication, it's very hard to get real-time disturbance information. And secondly, is that the optimization tool is a computation tool. It requires heavily iterative communication and computation to solve it, and then take action. Probably by the time we take action, it's already late. So the question is, can the load response in real time? And I say closed loop, that's kind of control dragon. It means, can we just based on the local measurable measurement and take action? So answer is yes. So we can understand the network dynamics, and thus we can design the controller. So what kind of dynamics it can help? So just a brief background about dynamics I'm going to use. So this is the frequency dynamics, like people call swing dynamics of like the dynamics of the frequency. So like all variables are physical variables. Mi is inertia, omega is frequency, PIM mechanical power. This is frequency sensitive load, and this frequency sensitive load, and this is the power flow. So you don't need to remember the details of what the variables is. So the thing I want to say is this is physical dynamics. We don't need to do anything. It's already given by the physics systems. And again, like I said, it's a network. Once a dispersion happens, it's going to affect my neighbor. So this power flow formulation tells once the frequency at one location changes, how it changes at the other bus. And put them together. That's what we have. This is the physical system. We haven't done anything yet. So we have frequency dynamics, we have power flow, and when this disturbance happens, we want to think about how to design the load. And what's the goal? The goal is to coordinate the load to solve this optimization problem, to make everyone, like balance everyone's cost and utility. So what's the solution? So I'm not going to say how we find the solution. This is the result. So it's very simple. At each bus, each load only measures the local frequency, omega I, and then use their own local utility function. Think about what's the new DI, take the action. Together, it actually solves the optimization problem. So the new part here is very simple. Everyone, even don't need the communication, just simple measurement, measure the frequency, and then take action. So when I say solve, what exactly means? It means it's asymptotically converged to optimal solution. And an interesting, surprising thing is together, system dynamics plus load control together is a primal dual gradient flow. Since everyone understands the primal dual gradient, you may be wondering why is the dual variable here? Here, the frequency dynamic self is actually a dual dynamics for this algorithm. So now once we found the connection, when we think about how to implement, it's a very simple one, like each bus measure frequency, take action, and then just goes. The message is frequency is actually a natural signal to coordinate all the device, and this one completely decentralized, and no communication is needed. And we did, when we do theory, we always make assumptions, simplify the model, linear approximation model, and how it works in practice. So when we use the full nonlinear model, the full power system simulation toolbox, and just plug in our controller, the simulation tells us it works very nice even with a complicated physical power model. And this is frequency dynamics. And we can see this is our controller. It can help the system frequency a lot. And this is the cost. It's really chasing the optimal cost of the load. So in summary, what I showed is this. We have a network physical dynamics. We have a mathematical optimization problem. And the question is, how are we going to design the controller to solve the optimization problem? So when we first get the result for the power systems, one question to ask is, what is special of the power system? is the tool general enough to apply to some other physical systems? And that narrows down to understand the network dynamics, what are the special things about the network dynamics. And then with continuing, put in a more general framework, we are able to apply this one to a more complicated scenario, like if we want to achieve additional performance for the controller, and we are able to do that. And another question is we want to understand the specialty of the systems. So we are able to find the sufficient necessary condition for the physical systems. So now, in the future, once I have the dynamics, I'm going to check the condition. If satisfied, then that means I can use the local measurement and solve the optimization problem. And it's a powerful tool for many physical systems, thermal control, generation control, and along many others. So I have showed one example about load frequency control. As in order to motivate it, the second one, how the mathematicals can also help, like quantization going to help. I'm going to switch to another one, is the power allocation within a building. So this problem is actually simpler. So now we assume this big building, we have some control center, some person is in charge of all the coordination of the device. What they want to achieve is to make sure everyone is satisfied, maximize the social welfare, minimize the cost, and make sure the systems is not going to have blackout, satisfy the safe operation constraint. Again, when we look into all the optimization tool, what is usually done is this. Step one, appliance can send a request, and control center can send back information, say, please reduce or you can increase. So this is an iterative process, and it's usually assume perfect or reliable, ubiquitous communication in the systems. The question we will ask is, if we think about the building, simple thing to do is probably the control center just broadcast some signal to coordinate. If I ask all the device had feedback information, that's probably too much. The first one, is it possible to just broadcast information? I don't need feedback from the users. Second one, even for that, how much information I need to broadcast? That's a question for this problem setting. And why we care about communication too much is when we look at the zoom into the data center, and also even for one laptop, the multi-core processor, the message from the computer science is the communication usually costs much more compared with the computation. So let's look at mathematically what I'm talking about. Very simple setup. Individual device has a cost function or utility function. Control center has a limited power to allocate. Now they're going to talk to each other, try to find the optimal solution. And this is textbook, problem, use the dual gradient descent. We're able to solve it. For the dual gradient descent, control center send a price, and price, individual users update their action and send a request. And under convexity condition, Lipschitz condition, this dual gradient descent going to converge. So let's look at the question that said, is it possible to remove one-way communication? And for this one, because it's so simple, we look at, this is a summation of the QI. What summation of QI? Is it just how much power is really consumed within this building? If we ask each device just real-time take action, what this means is I can replace this one with the just true measurement of how much power is used. So this is a very simple observation, but what's the problem here? So now I ask people to take action, and it's now sending the request, take action, I'm going to see how much QT is in total consumed. If it's lower, update the price. If it's higher, also update the price. The problem is if I do that way, it's going to violate the physical constraint during the transient dynamics. Because now, just I take action, or I already take action. So that's probably cause a big problem if I really care about the system not going to blow up. Interesting for this problem is if we are able to set the step size and initial setting carefully, and actually we provide a way to set up step size and initial setting, this constraint will hold all the time, even during the transient dynamics. And the reason why it's able to do so far for this problem is still like one-dimension problem. So actually for the one-dimension resource allocation, it's actually a lot of properties that we can use. And also we have a lot of result about convergence rate. Another thing is we really want them to converge faster. So, but let's go to the second one. It's like now we reduce the communication just one way, broadcast information, people receive the information, then to coordinate. And how much is needed? If I'm just using, since all the device is already wired together, I can just using the power line communication, send a very simple information to coordinate. How much is needed? So that's a question we want to ask here. How much is needed here? How are we going to reduce the communication? We look at the price information. It's based on the QT minus Q, whether we have more power or less power. What this says is only the sign matters. I don't care about exactly how what the price information. You just tell me, is this okay now or not okay now? So we just send indicate information, like 0 or 1 or 1 minus 1, depending how you're going to interpret the signal sent to you. By using that binary information, if I'm higher, sending 1, lower, sending minus 1, and I will ask individual person just keep a local estimate of the price. That's what I mean by recover information through local computation. I'm not sending the exact price information through the control center. Individual person keep some track of the price information. So this algorithm, even we're starting from the quantization, and if we look at the one-dimension problem, it turns out it's just the normalized gradient descent. Normal gradient descent is, instead of doing the full gradient information, just take the direction. If the problem is just one dimension, it just narrows down to the binary information. The problem is here is, I used a very simple example to illustrate our idea. The hard part is when we're really talking about the resource allocation, we have a lot of constraints, not just total power smaller than Q. We have a transformer at different kind of location, we have more constraint. So the more constraint, when we look at the dual part, this f is a dual function. It's going to be a multiple dimension. For the multi-dimension problem, now we call it a quantized normalized gradient descent. Is how we're going to quantize. Now we have so many constraints we want to worry about. How are we going to quantize this information? What is needed? So for this setup, f, think about is a dual function, a cost function you want to minimize. And the quantized, I put the normalized gradient descent because it helps us to understand the fundamental limit of communication. Like first, just think about direction, not about the magnitude. And this is dt, the d, the quantization set. So far, I'm using the static quantization. Each time, the same quantization is easy to code. And rd dt, and how we're going to set the quantization set. So first question is, to ask the question is like, how are we going to define a quantization is good? And what do we mean by it's good? So now it's a physical problem is I'm going to have some preset up between the control center and all the device. All the people can change their utility function. That means the f function is not specified. I don't know. People probably today and tomorrow, they are different. So when we define the good quantization, so we want the quantization scheme can work for a broad class of function. So that's how we define, like when the quantization is good, we call it the proper quantization, is this quantization algorithm going to converge for any well-behaved function. And so far, what we are able to do is for convex and smooth function that we have a result about how we're going to quantize. So now we have a definition for what is a good quantization. So this is a list of questions that we would like to answer. First is how we're going to determine our quantization is good before really running the algorithm. And secondly, what is the minimal size? So we want to ask the fundamental limit question. What's the minimal size of the quantization? Once we know the quantization is good, how are we going to use the quantization? The last one, we can imagine if I can have more communication, I'm going to achieve better performance. So what's the connection between the fineness of the quantization and the convergence of the algorithm? So this is a list of questions we would like to answer. Let's look at the first one, how to determine a quantization is good. So like, I would like everyone, since it's a simple gradient descent, I think a lot of intuition, also when we think about this one, is as long as it's descent direction, it should work. So with the descent direction, say this is a quantization, have a 3 direction of the red lines. And why gradient method works? Because the gradient method is a descent direction. And now how I make sure the quantization direction is still a descent direction, as long as I can find a direction that is close to the true gradient direction. So that's the intuition behind it. And now the question is the intuition exactly the sufficient and necessary condition for us? And the answer is yes. So for the problem I've shown, like even multiple dimension but non-constraint, the intuition just help us to develop the sufficient and necessary condition. So we call it the CETA cover. What CETA cover means is given a quantization set is already given, and we pick any direction in the surface. As long as we can find a quantization direction that within a small angle with the quantization direction, then the quantization should work. And we call it the CETA cover. Given this proposition, so what we are able to show is answer the question, what's the minimal quantization? The minimal quantization is the case dimension of the problem. It's only need the dimension plus 1. Now we look at how much information is needed is log. I think this has some similarity with what Keith presented this morning. Like once you do the distributed mean estimation, and the answer is also log of the dimension. I think the intuition probably similarly. I haven't checked the paper, but I think probably the intuition is similar. So this is actually very positive result. Is like only in log of the dimension, then it's good enough. And here, remember, the dimension is different from this morning talk. So this dimension is how much constraint we have in the resource allocation problem. And we have a lot of convergence result. Like if you give me different stopping criterion, how much iteration is needed. And I just give one example. So this example, because this is easy to check. So when the gradient is small, because the gradient is just whether the constraint is satisfied or not satisfied. So it's very easy from the control center. I know what I'm going to stop the process. I'm not going to stop the process. So here, this is a convergence scheme. And pay attention to the quantization, theta. And the result I'm showing cosine theta and cosine theta, and here. So we have many discussion about convergence rates in the paper. In general, what it says, final quantization, large step size is allowed, and final quantization, faster convergence. But there's a trade-off. Do we really want that much quantization? And how much bit is needed depending on the theta? That's a hard question. So that actually goes back to Shannon's very early paper. It's called the sphere packing. Because now everything next down to the angle theta. If I define the theta and how much quantization is needed, is given by the sphere packing problem. I think to the best of my knowledge, we only have the lower bar and the upper bar about the quantization. We don't have concrete connection between the theta and how much bit is needed, given if we're not talking about the minimal quantization. So, but here, let me use the example to show. Surprisingly, so here, f is a dual function, and we pick a 2-dimension problem. We pick a 2-dimension problem. This one, so this is a log scale. So this one is just gradient descent because we assume certain property of the problem. This has a linear convergence rate. But normalized, we call 3, this infinite bandwidth. This is a normalized gradient descent. The normalized gradient descent, you can imagine, because it loses the gradient, the magnitude information is much slower, become 1/t for that case. But look at the quantization case. Is mathematically have complicated connection between the fineness and the convergence rate. But from here, you can see 4-bit is almost exactly the same as the infinite bandwidth problem. So we don't need many quantization. 4-bit is good enough for this problem. And the gap between here and here shows it's not because of quantization problem. It's because we lose information. We didn't really put the magnitude into the quantization scheme. But that's a harder question because so far we didn't assume the gradient is bounded. If we're going to quantize adding the magnitude, we need an additional assumption about, additional information about the utility function. So back to here. So this is a summary of what we are able to do, given the simple gradient descent, non-constraint, but P can be multiple dimension. This is a question or task for you guys is can we extend the result to the constrained case? And if you say yes, you can raise your hand. Do you think it can be extended or not extended? I saw one, and my student raised a hand, like, who else agree it can be extended? So 2, 3, okay, anyway. But, okay, my answer is no. So all the very nice mathematical result, like once we go to the constraint case, doesn't work anymore. And we actually feel very bad at the very beginning, and why it doesn't work is just like simple constraint. So this is some intuition. So constraints actually really change many things. And so this is a 2 case. So for this case, okay, the gray color is a constraint. And this one is a current point. And this is a true gradient direction, and this is like, and the D is a quantization direction. So because of constraint, when we do the, and also here, because I'm doing this way, take the quantization direction and then to the projection. Because of that, when we do for this guy, if I take the closest quantization direction, it's this one, and this is perpendicular to the constraint. It means it's actually going to start at a non-optimal point. And for this one, it's going to say even if you like because of the projection to the constraint set, it's actually going not necessary to be the descent direction. So all the intuition we had for descent direction not going to work for the constraint case. And it's bad news. Why is it bad news? It's like we're doing the resource allocation problem, we have constraint. Always the constraint is smaller or equal. It's very hard to find constraint and say like if that's equal. So that's really bad news because if I want to apply for the problem I promised, I really need a constraint. So the good news is here, if we for this particular constraint set, because for the dual problem, we always say the dual variable is like positive or always negative. And for those problems, and do this specific quantization, and then everything works. So now what it says is for one dimension, 1 bit for one dimension. So in total, it's going to be, sorry, I changed the dimension again, like n bit or k bit is needed for that problem. And for this special quantization, we can prove similar convergence rate. And the interesting thing is this, we're actually able to apply the idea for real problem, like TPC flow control and optimal network, power management, and recently we had one very nice paper on the voltage control for the power system, because in the power system set, we would like to use the power line communication. If I'm doing the 1 bit, that'd be really nice. And we are able to apply the idea and to design a customized algorithm for the voltage control. So since we give a little bit of time, this is the last one, because in the abstract, I promised, we also study communication complexity. So what communication complexity means? I kind of fixed the quantization scheme. That means I kind of fixed the coding scheme already. So that's here. Like it's a binary, like everyone agree, -1 means that, like +1 means that. But in a more general fundamental question, if we really want to push the communication part, it's this. We're not talking really like fix the coding scheme. It can be anything. And also, since all the information, I have the information starting from time 0 to time now. I can use all the information to think about how I'm going to quantize. And for this scenario, I'm not going to show you the result. It's in the paper. So then we've kind of expired by the computer science literature is what the minimal bit is needed to achieve certain accuracy, what optimal accuracy is able to consume using the bit. And also the question is the complexity able to be achieved or not? Everything is available in the paper. And if you're interested, I would like to happy talk offline. In summary, what I showed is we have 2 methods to reduce the communication. One is use the physical system. The other one using the quantization information theory, like mathematical to help. The question is, when we talk about stable physical system, how to choose the right algorithm based on different setup. And you can see there's a lot of trade-off happening. Efficiency, robustness, communication, computation, so many dimensions. So that's really depending what the system operator is needed. And that concludes my talk. And before that, I would like to advertise my student poster. It's a very different topic. It's actually I think it's closer to the topic we have been heard here so far, like that setup. And we are able to design distributed algorithm for the natural. And I think so far, to the best of our knowledge, this is the best convergence rate. But we would like to happy take your feedback otherwise, like whether this is right or not right. Yeah, thank you.
In the quantization, did you apply some random dithering in the quantization of the gradient?
Yeah.
Is it random dithering or there's no?
So here, everything determinist. There's no random.
If you apply some random dithering, maybe then you can make this quantization as just some independent noise. And then this algorithm will be understood the same way as the category in the sense.
Yes. So far, everything deterministic. The proof techniques has some similarity with the stochastic gradient descent. And another thing, when we think about if you add randomization, probably you have another way to even reduce the communication, especially when you do the time variant coding scheme. Yeah. But here, everything we want for the communication, we assume is lossless communication. Okay. Thank you.
Questions?
Yeah.
Please.
So one constraint case, maybe quantization doesn't work, but you can still say that you are suboptimal up to a certain point.
Not really. Not really. You see the example we just hook up, it's usually was stuck. Yeah. Thank you. Thank you.